Welcome back, students. So we have covered up all our resistance based transducers in the previous unit number 1, and now in the unit number 2 we are going to go back to our induction based transducers. Induction based transducers. As we have already seen, in the classification of transducers, depending upon the mode of working, the transducers are classified into resistive, inductive and capacitive, and we have covered up the resistive based transducers, and now we are going to cover up the induction based transducers, which works on the principle of induction. Okay, the induction based transducers majorly worked on, you might have all known the what is resistance, inductance and capacitance. And what is inductance? Basically the inductance can be divided into self inductance and the second one is mutual inductance. These are the two things that you might have seen in the induction when you study in the basic concepts. But along with it, when a transducer works with an induction principle, there is also another one type of transduction possible, that is the eddy current induction. Eddy current induction. Okay. So today we will have a glimpse of all these three types of induction methods in which the transducers can work. Okay. First we will go for the self-induction based method, working on the principle of self-induction. The self-induction, when we talk about, immediately what law you need to remember, it is our Faraday's law. Faraday's law of electromagnetic induction. Okay, so this is the basic law that governs each and everything. A motor, a spinning motor, whatever it we have is being governed by this kind of the law, that is the Faraday's law of electromagnetic induction. And we have this, okay, law that governs the self-induction also, which states that when there is a change in magnetic flux, okay, through a current carrying conductor, then there occurs an EMF. Okay, to make you easily understand, I will draw a diagram. There is going to be a coil, this is a conductor, okay, and you are going to move there when there is a change in magnetic flux. Okay, so we are going to take a permanent magnetic bar and we are going to move it in and out direction continuously. We are going to move in and out. So there is going to be a change in magnetic flux around the conductor. Okay, then there occurs an EMF over here. Okay, an EMF will be generated here when there is a magnetic flux change. This is having a magnetic flux, this is a magnet, this is the coil, and because of this movement you are having an EMF that is generated. This principle is called as Faraday's law of electromagnetic induction, and now the transducers that works on this principle is called as the self-induction based transducers. So in this just a simple diagram itself, you are able to see that we are having an movement happening with the magnetic coil, not the magnetic, sorry, the magnetic rod, okay, that we are going in and out. So you can easily say that there is going to be a displacement, and linear displacement that is happening in and out of the coil. Okay, so now when you are able to go in and out of the coil, there is going to be an EMF, directly proportional EMF change. How much you are coming out, you are going to have a low EMF, and how much you are going in, you are going to have an high EMF. Okay, so that is the law, the self-induction based transducers. The next thing comes into picture is this can be taken for linear displacement. There are several other arrangements where you can change it into some rotational arrangements like this. okay, and then you can insert some uh, rotors, okay, movement, okay, which will give you the angular displacement also, that is possible. So there are several patterns available in this self induction based measurement. The next comes the mutual inductance. This is the most important type, the mutual inductance, where we will be seeing different most important transducer here in our classification. The mutual inductance, as you might have seen, this mutual inductance, when you talk about itself, there should be two coils. When there is going to be an EMF generated or a current carrying conductor is placed near the coil, an EMF is generated here also in the neighboring coil, because of the, here there should be an conducting area. When this coil comes nearby and go away, this EMF will rise or fall. Now this kind of a principle, that is, it is induced, we are not giving in an EMF here, this is an induced EMF, this is induced, this is the charge that we are giving in EMF here, and here this one produces an induction and it produces an EMF over here. This kind of an induction is called as the mutual. Okay, now again here you are seeing that when there is a movement of the second coil, this is the first one, this is the primary coil, this is the secondary coil, coming nearby, going away, okay, then there will be a change of EMF which is proportional to this linear displacement. So this is the mutual inductance, okay. So now you are clear with what is self-inductance based methods to method of induction, and how we can measure the linear displacement or angular displacement, we can use it. And also for the mutual inductance based methods, we are having an arrangement and then we can transform this into a transducer. So we all this angular measurement and angular displacement measurement, linear displacement measurement, we have seen in the resistance based transducers also, that you have to recall that what are the resistance based transducers that we have seen for linear and angular displacement measurements. Those are those that the first linear potentiometer or the translational potentiometer for the linear displacement measurement, and the rotational potentiometer or helical potentiometer for the angular displacement measurements. Recall these two things and then compare it with this induction based transducers. Here we use it for the self and the mutual inductance. The third one comes with the eddy current. When here it's a different case, you are having an current carrying coil or a voltage is having, you are coming with nearby a conductor, a metal piece comes near this coil, okay, you are coming near to the coil, okay. There occurs an opponent of the voltage that is present here, and an current is generated in the conductor which is here. You can measure the current value, and this opposing current that is generated, okay, will create a decrease in this voltage because it is an opposing current, okay. So that it will create an decrement in the voltage, and this decrement, okay, is proportional to the amount of current that is produced, and this current is called as eddy current. This current that is generated in the conductor is called as eddy current, and you need to measure the decrement that is happening, which is proportional to how much this conductor is nearby to this coil, okay, that you have to measure, and you can say whether how much the conductor is nearby, whether is it nearby this much or that, or it's away, and depending upon the direction of the movement of the conductor, you can easily say whether you are able to get the correct displacement value, and this principle is called as the eddy current based transducer. Okay, so now you are clear with this. First one is the self inductance based transducer, the for measurement of linear and the angular displacement. The next one is the mutual inductance based transducer for the linear and the angular displacement. You can convert this one, and then the final one is the eddy current based transducer. Okay, now we will jump on to the most important transducer, that is LVDT. Okay, that is a linear variable differential transformer or transducer. But based on the working principle, it is a transformer, but it is used as a transducer. Okay, so you see it's a huge name. It's for linear variable differential transformer. Okay, the linear comes with you are using this instrument for the measurement of linear displacement. So here the linear comes from. Variable, you are able to see it's not a constant motion, it's a dynamic motion, so it is variable, you can measure it. Finally, it is differentially, you are taking the output and it is working in the fashion of a transformer. Okay, so before going inside the details of the LVDT, you need to know how a transformer works. Everyone might have, a transformer works with the principle of mutual induction. Yeah, the same thing is the transformer. Here what we see here, this is a transformer principle. You will have a primary coil, you will have a secondary coil, okay, and finally you will have the EMF being generated from the secondary coil because of the induction that is happening for the primary coil. Okay, the same thing is here also, the same thing we are going to apply. See here, so this is our primary coil that we are going to supply in the voltage. Okay, then we have a core, a shaft that is moving in and out, displacement, this is the displacement, the linear displacement that we are going to give inside the coil. Again we have a secondary coil S1, this is P1, then another one is S2, and it is connected in this fashion. Okay, and we are taking in the output over here. Okay, so this is the basic principle of the linear displacement measuring transducer. There occurs a voltage over here, okay, and you are getting a displacement when the rod, when it comes inside, okay, and how much it is inside the depth it reaches the S2, then you will be able to get the higher voltage, and how much it is nearer to the S1 you will be able to get the lower voltage, and when it is in the mid position it will give you 0. Are you able to understand? When you put the rod in the mid position it is 0, okay, that is S1 is equal to S2, the voltage that is produced from S1, that because of the mutual inductance between the P1 and S1, and the P1 and S2 produces two mutual inductance values, the V values. Let us take V1 or V2, okay, I can write it here. The first criteria is when you put the bar to the center, then S1 voltage equal to the S2 voltage, then it is 0. Okay, then when it is nearer to the S1, then S1 is greater than S2, okay, then it is a positive voltage. Then when S2 is greater than S1, it is a negative voltage or the something in the opposite direction it is happening. Okay, are you now getting clear with what I told you? So initially it is put up in the balanced condition. Then when you pull the rod back, it will give you, when it is in the S1 coil, you are getting a positive displacement. When you put it in the negative direction, you are getting in the negative displacement. That is happening because of the mutual inductance between these two coil, and the output can be measured. Okay. Now I have told you in a theoretical fashion. We will now see the LVDT in detail with the in a practical manner. I will just unwind all these things and show you. So entirely the LVDT looks in this fashion. So this is a LVDT. This is an LVDT, okay, and the shaft is this. Can you see the motion that is happening? It is a displacement. It is now I have totally pushed inside, okay, and it is maybe reached the S2 coil level, and when I leave it, it is at the mid place, it will be having a 0 level. When I totally leave it, it will come to the S1 level and it will reach the outside. Okay, something like the 0 level will be here. Then if you press inside, it is S2. If you come outside, it may be S1. Okay. Now we can see even the inside how it is, the constructions are looking like. See here, inside you are seeing the encapsulation of the copper coil. Inside you see the encapsulation of the copper coil. Inside you will have the primary coil and the secondary coil windings, X1, P1, S1, S2 both will be there. The concentration of the S2 will be inside, the concentration of S1 will be at the outside, and the primary coil will be wounded at the center regions. Then here is your most important shaft. Can you see? See, this is the shaft, what is happening. As I told you, this is the shaft and the movement is given by the this one, and it needs to come back to its original position. So we are also providing it with a spring. It's a simple arrangement, but it is very sensitive and a precise arrangement to measure the linear displacement. See, I'm just putting it back and then I'm just winding it off. So this is now again, you can use it for the measurement of linear displacement. So now you see again, we are having it, the shaft is can be used. Now we can connect anything here, any kind of a displacement. When you want to measure how much I am moving my hand, we can easily connect this terminal to a computer, and then you can measure the microcontroller or anything, you can measure connect it, and then you can measure the displacement, how much it can measure. But you can very well see here the displacement maximum is 1 centimeter, that much only you can measure with this. But depending upon the length of the LVDT and the shaft thickness and the materials, the properties may also vary. Okay, so this is the main, all those things are, it's a very sensitive instrument, very precise instrument, that it can measure till the range of below millimeters, or in micrometer level it can go for the measurement. Okay, so this is the main advantage of an LVDT, that is a linear variable differential transformer. For the measurement of rotational variability, we have an instrument known as RVDT. RVDT, that is rotational variable differential transformer. Okay, that's also working on the same principle of mutual inductance, but the construction of the instrument is little different. Okay, here the primary coil and secondary coil are put up in the linear fashion. There it is put up in an, this is the primary coil, okay, and a shaft will be taken and it will be moving inside, okay, using an outside layer, and inside it will have a secondary coil winding, okay. Next class we will detail discuss about this rotation variable differential transformer, and I will discuss how it can be measured for displacement oriented applications. And but to first, as a summary, I will summarize as we have seen the linear variable differential transformer which works with the principle of mutual inductance, and it's a very precise instrument and it can be used for any type of linear displacement measurement and for calibration purpose. Until now we can using it for different kinds of many applications, starting from the measurement of a small movement in the precise movements inside some conveyor belts to even creation of large huge waves when you want to put it in a pool in a research. There also you can use. We are using these things inside IIT Madras Ocean Engineering. Also they use this kind of big huge LVDTs for creation of calibration and creation of displacement, that is production of waves. So thank you very much, and we will see with the next class soon. Thank you.